and welcome to today's episode of the OUR Path to Research podcast. We're excited to have you join us today for an episode exploring the intersection of AI and health research in the world of antibiotic development. My name is Hannah Kim, I'll be your host for today.
And my name is Paula Agudo, I am your co-host.
Today we're excited to have two PhD students for Dr. Stokes Lab.
Awesome, yeah. My name is Jeremie. I'm a PhD student in the Stokes Lab. My research focuses around the use of AI and computational methods to kind of accelerate antibiotic discovery. But recently also kind of dipped my toe into anti-cancer and antiviral discovery as well.
My name is Stewart. I'm a PhD student in the Stokes Lab, and my research focuses on discovering new antibiotics that are resistant to resistance, or in other words, have a lower propensity for resistance development.
So the work going on at the Stokes Labs is truly fascinating, but before we get into all of that, we want to make a quick rapid fire round of questions. So just brief questions to the work as icebreakers. And so I'll read them over and you can take turns answering. All right, let's go. Could you describe the Stokes Lab in 3 words?
Ooh, okay, so I got this one. Exciting, fast-paced, and novel.
Okay.
Yeah, I would say fun, loud, and innovative.
Cool. Sounds like a pretty cool environment. Now, if the lab had a slogan though, what would it be?
Probably work hard, play hard.
Okay.
So we do have a slogan. We have these hoodies that say "really good science," which is what we're all about.
Awesome. And then, how about you? Do you prefer working in silico, in vivo, or in vitro?
So for me, I love an in vitro in silico combination, but I mainly focus on the in vitro work with bacteria and mammalian cells.
Yeah, I'm mainly in silico, but recently I've been trying to get more into the in vitro side of things because I think AI is going to do all the in silico stuff for us, so trying to get a job later.
Okay. Thank you so much.
Awesome.
Could you explain your research and tell us about how AI is used to discover antibiotics?
Yeah, for sure. So I guess starting from the first part, normally what we'll do is we'll collect training data. And so that looks like anything from screening a bunch of compounds against a bacteria. So essentially measuring if the compound can kill or inhibit the growth of the bacteria. And then from there we take that data, we about 10,000 to 20,000 compounds. And then we can teach a model to learn what structural features specifically are associated with killing a bacteria. And then once we have that model trained, we can then screen millions to billions of compounds in the computer to try and find stuff that shares some kind of antibiotic substructures with what we learned in the training data set. And then from there we can just prioritize a top 100, top 200 compounds in the computer, order those. And then normally those will have a higher hit rate than if we had just taken 200 random compounds off the internet. So it's just really a tool to kind of streamline what we're doing. It's how can we get to promising chemicals faster, so that we actually have fun stuff to do in the lab and we're not just getting a bunch of chemicals that don't work. So that's pretty much the gist of it. But I'll let Stu anything else.
I'd say that was a perfect answer. So,
yeah.
Okay, that's really fascinating. It sounds like a lot of complex work.
Mm-hmm.
The podcast is made for undergraduate students who are looking into getting into labs and getting research experience. So we would love to know, what are the key points in your academic journey that led you to working in the Stokes Lab now?
Yeah, so I guess for me it started in high school. I got super fascinated with bacteria and antimicrobial resistance. So this led me to do an undergrad at University of Guelph in microbiology. And there they had a super cool program where they focused on natural product discovery of antibiotics. In your 3rd and 4th year, that was kind of the gist of your lab work, was discovering new antibiotics, running your own projects yourself, which really got me intrigued and farther into antibiotic discovery space. I ended up in Eric Brown's lab for an undergrad. I did a co-op there and then the summer internship. Met John Stokes. We hit it off, and I loved his work, so I ended up joining his lab as a PhD student. So,
Yeah. Also, similar to Stu, I also didn't go to Mac for undergrad. I went to Queen's. I did the biotech program there, and I think I was first fascinated by microbiology specifically, just learning all the things that microbes can do, the crazy places they live in the environment, the crazy things they do, how they've evolved to do all these things. So my 4th year thesis was actually in trying to isolate enzymes from microbes that can break down plastic. So a lot of protein purification, a lot of like enzymology and everything. And then I got really tired of trying to purify proteins, and then said I would rather just work in the computer and then I don't have to deal with all this stuff. So it was kind of a perfect, I guess, option. John was like just starting his lab. Obviously found the antibiotic stuff. It was still in the microbiology realm. Found that super interesting. And then joined mainly as an in silico student. But yeah, I've always been interested in the in vitro side of things, and so Stu's been teaching me all the techniques of how to get back into the lab. So yeah, overall it's been good.
Really cool.
That is really cool. It's a lot of mentorship and also hands-on work. So thanks for sharing.
I'm sure there are many, but could you tell us about some ongoing projects in your lab that you're most excited about?
Yeah, for sure. Which one do I talk about? So I think something, I'll bring up a recent project that Stu and I have been kind of trying to ideate a little bit recently. Like in antibiotic discovery, there's kind of two ways about doing it. You can kind of expose a whole bug to a drug and see if it kills it, or you can try and bring it down to the protein level and see if a molecule specifically can bind to or inhibit a protein, right? So those are kind of the two extremes, where you might get a lot of stuff in that first option that is just toxic to normal cells, and you might get a lot of stuff inhibiting proteins that aren't active in a whole cell context. And so Stu and I have been trying to think of like ways to kind of come up with hybrid approaches where we can do these whole cell screens, but then at the same time get some sort of mechanistic understanding of like what the actual bacteria or the molecule is doing. We have a project right now kind of focused on that we're really excited about, and then potentially we see if we can screen enough molecules and get enough data, potentially train models to try and expand our hit space. That's a project or a direction I'm really excited about. Let's talk about this as well.
Yeah, so that project, super cool. It's in its early stages right now. We're trying to optimize the screen, but we also have some other super cool projects coming out, one of which is the escape model, which I'm somewhat a part of, but it's actually mainly focused, or I guess the person who's running it is our PhD student, Autumn Arnold. And it's a super cool tool where we screen 7 different pathogens called the escape panel plus a knockout of one. And so we screen this panel against 3,000 or 2,500 molecules and then trained machine learning models for each bug. So we can then use this to predict narrow spectrum antibiotics and broad spectrum antibiotics. So if a prediction has activity or has predicted activity in all of the bugs, it could be a broad spectrum antibiotic. And if it only shows activity or predicted activity in one of them, it could be a narrow spectrum antibiotic. So Autumn has released this tool as a online website which anyone can access freely and easily too. All you need is a string of smiles, so this representation of a molecule, and it will predict on all of these models for you and tell you if this molecule has antibacterial activity or proposed antibacterial activity. So super cool project. You should check it out. It's escape.mcmaster.ca.
Perfect. Thank you so much for explaining such complex processes in like a way that we can understand. I love how it's making a real difference in the health sciences and medicine.
Shout out to Adam too, the escape model.
Yeah.
I saw it on the webpage. It looks pretty cool.
Yeah.
Now, the Stokes Lab deals with so many different trials. You have anything from cell culture, then I saw preclinical in mice, then a lot of computational biology too. Is there any skill that is particularly useful for the work that you do in the lab? And if so, how did you get it?
Yeah, so there's definitely a lot of useful lab techniques that you can learn. But one of the basic skills that we do essentially on a daily basis is called an MIC. So essentially it's a serial dilution technique in which we test what is the lowest concentration of our drug that will kill a bug, right? So this will incorporate using pipettes to handle liquid, multi-channels specifically, so these pipettes have 8 different channels in them, so we can do things efficiently. So lab skill, learning how to do serial dilutions and MICs is like one of the main things that we do and would be very useful for anyone who is doing work in the antibiotic discovery space.
Thanks.
And I guess kind of like moving into the in silico stuff as well. I would say like getting like a fundamental like machine learning and AI and how to kind of work with models. And I think it's especially pertinent for undergrad students who may not have access to like lab space and be able to do stuff, because I mean anyone can run code, anyone can write code, and so if you're an undergrad who's like interested in research, like just start learning Python and start learning how to kind of get into machine learning and start coming up with projects that you can start building that might teach you of how to like train models and predict on stuff and everything. So yeah, I would say that's the biggest advice for an undergrad that's looking to get into research.
Amazing, thank you.
Could you tell us how you moved from something like a computer prediction to something tested in vitro or in vivo?
Yeah, for sure. So like that sounds really easy, but it's actually really tough. So like one of the big things, the big challenges is like it's really easy to design chemicals in the computer, and they look super nice in the computer. Like wow, that's a really nice molecule. But then when we give it to a chemist, they're like, oh shoot, like this is going to cost like $5,000 to synthesize. And so I guess like a big thing our lab's been focused on is like trying to enforce synthetic accessibility like early on into the like design process, such that every molecule we make, we can send off to a company and they're like, yeah, $100 and we'll send it to you in whatever 3-4 weeks. So I would say that is like kind of the biggest challenge. Like we'll design something, we'll cross-reference it with the company's database. And the company will normally say, yep, I can make that, no, I can't make that. And then within 3-4 weeks, we get a bunch of vials of compounds right at our doorstep, and then we can just put them into bacteria and see what happens. So I would say that's the overall process.
Yeah, and another thing that we could add to that is, once we have these molecules that are synthetically accessible and cheap, is filtering down, right? Because we can still have 10,000 molecules of the space that are synthetically accessible and cheap, and we don't have, $100,000 or $1 million to spend on ordering these 10,000 molecules. So we need to find a way to shrink it down to a size that is accessible for us, 100, 200, 500 molecules. So to do this, we can also remove, molecules that have known antibiotic structures, so that aren't novel and would be already resistant to, or already, they wouldn't be effective against resistant bacteria. We can also remove molecules that look similar to one another, right? So if we have two molecules that are like enantiomers of each other, it's best that we just order one so that we can explore the largest chemical space with the smallest number of molecules, right?
What part of this process would you think that students are most surprised about?
Yeah, I think like just the speed of like computational versus like wet lab experiments. Like being able to run like in silico experiments, like you can get enough data to almost publish a paper within like an order of weeks, like because you're just like running predictions, you're making models, you're like all of these in silico metrics are so easy. So you can almost build up, like say you have a 4-figure paper, you can build up 3 of those figures in probably 2 weeks. But then when you bring stuff into the lab, then that one figure will probably take like 6 months. Yeah. So like I would say the biggest surprise for me, that was the question, right? Surprise. Yeah. Was just like the difference between like the two research realms. Like they're so different in terms of speed. And so yeah, I would say that was the big surprise for me, but I'm sure you have something different.
No, I mean, for me, it was the opposite. So I started out in doing in vitro work, whereas Jeremie was like big into the in silico work at the start. So I had the opportunity to train my own machine learning models for my project, and yeah, I was amazed at the speed of what I could get work done. Right? It was like, oh, I, spent 3-4 weeks collecting training data to train my model, and then I've explored a space of, I think it was 20 million molecules in 2 weeks. So just the vast speed that we can use these in silico approaches to enumerate chemical spaces is amazing. It's super surprising.
Oh, wow.
So, yeah.
Thank you.
Yeah, 20 million molecules in a wet lab cannot be analyzed in 2 weeks. So that is pretty impressive. And I also like how you highlighted not only, running the models, doing the trials, but also making them accessible, right? Because that's the end goal. We want to get this into people. We want to move healthcare forwards, right? And finally, we would love to touch on antimicrobial resistance. And why is it such a huge problem nowadays? As well as how is your lab working to target this problem?
Yeah, so what is antimicrobial resistance? Essentially, it is when a bacteria becomes no longer susceptible to the treatment of an antibiotic, right? So right now, I think it was, the estimate was 2021, there was like 1.1 or 1.2 million deaths directly attributed to antimicrobial resistance. And it's predicted that by 2050, we'll see approximately 10 million deaths per year that are associated with antimicrobial resistance. this is, the exact, around the approximate number of people that die because of cancer, right? So it's a growing problem if not addressed immediately, right? What do we do different to somewhat circumvent AMR is through our filtering process, essentially. When we're in silico screening molecules, we'll find 10,000, 100,000 that are really cool. And then we remove all the ones with known antibiotic scaffolds. And in doing so, we're eliminating the possibility that the molecules that we bring into the lab already have known resistance mechanisms that are present in the environment, in the clinic, in a hospital setting, wherever, right? So this is one way that we're hoping to kind of skirt around AMR to, I guess, develop novel antibiotics that are actually effective when they're given to a patient.
Yeah, 100%. Yeah, I mean, just to echo everything Sue said about antibiotic resistance, it's becoming a big issue. A lot of our current drugs that we're using are becoming increasingly active against a lot of these pathogens. And I guess one thing we're trying to do in a sense is we haven't really come up with a new class of antibiotics for the last 40 years. There were two recently, but excluding those, it's been about 40 years. And so we really need to kind of bolster our repertoire of new antibiotics so that if someone comes in with an infection that literally can't be treated with anything, we have something that we can actually give them. So I think at the core, we're just trying to find a quicker way to get to promising chemicals, such that we can maybe accelerate the first part of antibiotic discovery a little bit. So ultimately, when we go into more of the clinical development stages, we have more candidates that we can bring in, and then hopefully increase our success rate if that's something actually is successful. And so I would say that's the big thing that we're trying to do. Yeah.
Of course. And thank you so much for all the work you guys do at the lab. And thank you so much for being here today as well. And with that, we've reached the end of our podcast episode. We hope you have enjoyed it. Thank you so much for being here, and thank you so much for tuning in. Feel free to follow us on social media, as well as visit the Office of Undergraduate Research website. You can also give a shout out to your social media if you would like to.
Yeah, we have our Instagram account. I don't know if you guys I'm sure some people have seen it, but trying to make science a little bit more fun. So yeah.
What's the Instagram handle?
The Stokes Lab, all lowercase, no spaces.
Amazing, thank you. So make sure to check them out. I'm sure you will like the content. And for our next episode, we look forward to talking with the Jubella Lab in kinesiology. But for now, this is everything for today. Thank you for tuning in.
Thank you.